Okay. So, this is the second last lecture this year. We're going to finish off by completing the discussion on waveguiding in this dielectric slab. And finally, I'm going to give a brief repetition of the whole course. So, that's the plan for the remaining lectures. The system that we were discussing was this dielectric slab, which is basically a dielectric with a high index of refraction, N1. And it's sandwiched between two other media of lower indices of refraction, N0 and N2. In principle, you could have air on both sides or glass on both sides or whatever. The point is just that this and this index of refraction is low, and this film in the middle has a high refractive index compared to the two others. And here, D is the thickness of the film, okay? So it stretches out in the X2, X3 plane in infinity in both directions. And it's quite small in the X1 direction. That is, it's a few micrometers or a few wavelengths if you want. And we made an ansatz for the electric fields and the magnetic field. Which was some vector which depended only on X1 because we have invariance in X2 direction and propagation in the X3 direction. And the B field has the same form. Okay, now we notice that with this ansatz for the fields, D3 is simply I beta. So I can replace any occurrence of this operator by the constants I beta. dt is minus I omega. And finally, d2 is equal to 0 because there's no x2 dependence anywhere because we have invariance in this direction and we're propagating in the x3 direction. Okay? Yeah. Now this looks a bit like a plane wave, but the dispersion relation is different, and we're going to find that dispersion relation today. By the way, this beta guy, that's what we called k parallel before, so I guess I should have stuck with that, but I didn't for some reason. So that's equal to some, let's see, n, which is an effective refractive index times 2 pi over lambda, where this is equal to omega over c. So this is the vacuum wavelength of the light, and this is the effective index of refraction for mode M. For mode M. And we'll get back to what this mode M means towards the end when we found the dispersion relation. Okay? And in the last lecture, the only thing we really discovered was the following, that if you use the curl equations, and the Ampere's law. By the way, I'm assuming linear isotropic homogeneous material, so H is simply mu naught B, and D is epsilon E, so no difficulties there. These two equations on component form show us that we have two types of modes. We have the TE mode, which is that we have a transverse electric field, so there's only electrical field in X1 or X2 potentially, but we showed that in fact we only had E2 and then B1 and B3 mixed in those equations, but they decouple from the other components. We also have a TM mode, which was B2, E1, E3. So for the TM mode, these three field components decouple from these field components. Everyone remembers what T and Tm stands for? No? T stands for transverse electric. That is that the electric field is completely transverse to the direction of propagation. So the T is transverse. So let's have a look at what transverse electric means. If the propagation direction is x3, well then the field is completely transverse to x3, meaning that it could only have a component along the other two axes. Okay? There's no, transverse means there's no component along the propagation axis. But from the equations we showed that E1 and E3 couple. So you can't have a TE mode with an E1. Okay? So the definition of transverse is just that the field is transverse, but the equation showed us that if the field is to be transverse, it has to be only pointing in x2 direction. And same for the magnetic field. If you're going to have a transverse magnetic mode, you can only have a B field component along x2. Okay? Made it clear? I hope. Okay, no one is complaining. So that's what we showed last time. From now on, we're only going to discuss the TE mode. And TM mode, that's homework, if you want to learn more about this. The procedure is basically identical, so it's not, there's not so much new physics to learn, but you learn the, well, you learn how the calculation goes when you're going to find the dispersion relation. And now if you're going to find out how these waves propagate, we're going to start looking at the wave equation, which we know has the form nabla square of E2 minus n square over c square dt square of E2 is equal to 0. And of course, I assume that we have no currents, since this is a dielectric, and that we have no charge accumulation of any significance. You'll notice that we only need the E2 component because I only work in the TE mode, right? Okay. Now let's have a look at this guy. What's that? Well, that's d1 square plus d2 square plus d3 square. And that is equal to d1 square plus 0, because there's no x2 dependence, minus beta square. Okay, and now I can just insert this here. And we also recall that dt was simply minus I omega. So let's see, dt is equal to omega, like that. And that gives us the equation that d1 square E2 of x1. And here we see why we only have x1 dependence. Let's see, and then plus n square omega square over c square minus beta square E2 of x1 is equal to 0. Okay? So this x3 derivative was particularly simple, along with the x2 derivative, which gives us basically a one-dimensional equation. Okay? So now this is actually, it's not even a partial differential equation anymore. It's simply an ordinary differential equation. We have the derivative, or second derivative, of E2 plus a constant times E2 is equal to 0. And this is an equation we know very well how to solve. So I'm basically going to just quote the solution. We have to consider two different cases, because this constant here, which I'm going to call gamma square. So perhaps I write it up here. Gamma square is equal to n square omega square over c square. This is the wave number in a large slab, but we're going to see that in a small slab or a thin slab, then we're going to get some confinement effects from this beta. So we include that here, beta square. Now this is basically the differential equation, d dx1 square e2 of x1 plus gamma square e2 of x1 is equal to 0. All right, doesn't look so hard. Although we have to consider the two cases here of gamma. So the first case is beta square larger than n square omega square over c square. In that case, gamma square is negative, meaning that gamma itself is purely imaginary, which gives a gamma of plus minus I beta square minus n square omega square over c square. I simply flip the signs inside and take out the I explicitly to prove the point. While in the other case, then gamma is simply plus minus the square root n square omega square over c square minus beta square. And if you recall our discussion of plane waves incident on an interface, these are the so-called evanescent modes, and these are the so-called propagating modes. Okay, so let's just reveal right away that we're looking for solutions where we have this case in the film. So gamma f, that's the gamma in the film. And we have solutions on this form in the air and in the substrate. So gamma air and gamma substrate, they should be purely imaginary. Because we're not interested in those waves that are propagating, because we discussed those before. We're only going to look at the modes where you have propagating in the film and evanescent in the air and in the substrate. Any questions? Someone looked a bit skeptical. Ja. Well, the question was if this isn't propagating or sine-shaped solutions, and this should be exponential solutions. But if you notice here, this is this beta. If you look at the definition of beta, so to speak here, this is beta. That's the wave number in the propagation direction, right? So that's k parallel from our previous discussion. So we recall that to have a propagating mode, you needed a k parallel which was smaller than omega over c. Otherwise you get this evanescent behavior. If you solve this for beta, then you'll have a real number and an imaginary number, and that will give you this attenuation behavior. Right, if you insert over there, and then you get, well, I think we'll get to this. Let's see. Well, you might say that in this equation, I'm guessing on the equation on solutions on the form e to. Well, maybe there's a sign error somewhere, but well, I think we'll get to the point. I have bad experience trying to figure out the sign errors while standing here, so I think we'll get to the right conclusion anyway. Okay. So neglecting sign errors to first order, we have the solution to this equation. The first type of solution is, as you said, exponential solutions. E2 of x1 is equal to c e to minus gamma x1 plus d e to plus gamma x1. And these are the solutions we should have in the film and in air. Okay? The other type of solution is that we have, let's see, E2 of x1 is equal to A cosine of gamma x1 plus B sine of gamma x1. And this should be in the substrate. No, sorry. I'm all wrong here. It's substrate and air and film here. Okay, and I think this is right because if I insert this into the equation now, when I take the double derivative, I get out a minus sign, right? So this is negative, which means that the terms cancel. Sorry, this is negative, so the two terms cancel and we get 0. Sounds right? Okay. And now, of course, the problem is reduced to finding, yeah? Mm. Så skal vi se, hvis du har en ja, du har rett i det. Nå skjønner ikke jeg hva som er galt. Jeg har en i fra før av. Ja, jeg tror det er der det ligger. Ok. Men ja, det er mulig at jeg visste hva svaret var, og ikke det hender det regner sånn, at man vet hva svaret, og så surrer den på veien dit. Ok. Okay, so there's a gamma here. Anyway, to get a propagating mode, you need this condition to be true that you have a real gamma. No, sorry, you're right. There's an I here. So, Now, I think we'll just continue on this form, and then we'll say that there's a sign error here, but we'll neglect it. Okay? I'll get to the point anyway. This isn't the best Monday this year. I forgot to bring pants to work today, so in a long line of unfortunate events, I didn't have time to prepare very well, so I'm sorry about that. Anyway, now, as I said, to get A, B, C, and D, we need the boundary conditions, because those are important, right? They will constrain what kind of solutions we can have. And the boundary conditions are as follows. The electric field will have to go to 0 as x1 goes to plus minus infinity. So if I go away from the dielectric slab, I will have no field. I'm saying that the field should be confined to the dielectric slab. Okay? So that's boundary condition 1. Boundary condition 2 is that E2 in air, when I go towards x equals d from above, is equal to E2 in the film as I go to x1 equals d from below. Okay? Third boundary condition, E2 in the film at x1 equal to 0. Well, that has to be equal to the field from the substrate. So E2 in the substrate at 0 will have to be equal to that. Recall that E2 is purely tangential to the surface, and the parallel electric field is continuous across any interface. Let's see. Now the next boundary condition is that B parallel is continuous because there's no current anywhere, and we're assuming that mu is equal to 1, or mu r is equal to 1 everywhere. Meaning that B3 in air at D is equal to B3 in film at D, same as the electric field. And we also have B3 in the film at 0 is equal to B3 in the substrate at 0. Now, let's see. Recall from if you go back to the let's see, to Faraday's law, this one. And if you write that out on component form, then one of these components looks like the following: minus dt of B3 is equal to, let's see, d1 E2. Okay, so I can write these two boundary conditions. Instead of writing them in terms of B3, I can write them in terms of E2 instead. And that's the component I have solutions for, so that's very convenient. So our boundary condition number 4, that must be simply d1 of E2 in air at D is equal to d1 of E2 in the film at D. And finally, boundary condition 5, that's this one. So that's d1 of E2 in film at 0 is equal to d1 E2 in substrate at 0. Looks right. Now, from the boundary conditions, we can start to make some preliminary conclusions. In air and in the substrate, we need to choose those solutions which are exponentially decaying. Okay, so in air, E2 in air of x1, I can write that as follows: C E2 minus gamma A x1 minus D, like that. Okay. Because now we get an exponential decay as we increase x1. So if this is the film and we go up into the air, then the electric field decreases. This D I can introduce because it simply changes my C. I can write this as C E2 minus gamma A x1 times E2 minus gamma A D, and I can just put that into my C, right? E2 in the substrate is similar, except it's decaying as we go downwards, so that's E2 gamma S x1, like that. Okay? Finally, in the film, which we're really interested in, we have E2 in the film of x1. Well, we can't really say if A is 0 or if B is 0 before we look at the other boundary conditions. So for now it's A sine of gamma F x1 plus B, sorry, that should be cosine, sine of gamma F x1, like that. Okay, so now there's, we got rid of the D here and the C here, so we only have 4 left. Coincidentally, we have 4 boundary conditions that we didn't use yet, so we need those to set up equations for A, B, C, and D. Okay. So as an example, if you look at, let's say, this equation at 0, the electric field is continuous. No, wait. Yeah, that means that let's see, at 0, this one is 0, so B times, A times cosine of 0, that's 1, isn't it? Is equal to, let's see, in air, no, sorry, in the substrate, at x equals 0, this is simply equal to D, so A is equal to D. This gives me the equation A minus D is equal to 0. Right? So that was this equation here. And setting up these equations, that's really simple, so I'm not going to go through the details. I'm just going to quote all 4 equations, because this is something you can do on your own. And if I just write that equation system on a standard matrix form, then we get the following equation system. So it's 1, 0, cosine of gamma f d, gamma f sine of gamma f d. That's the first column in the coefficient matrix. Let's see, and then there's a 0, gamma f sine of gamma f d minus gamma f cosine of gamma f d. It's 0, 0, minus 1, gamma a, minus 1, minus gamma s, 0, 0. Was there a question? No? Okay. Times the vector of unknowns, that's a, b, c, d, is equal to 0. So the right-hand side is 0. And if you recall your linear algebra, you'll remember that if you're going to have a solution that's non-trivial, that is, if not all of these are going to be 0, well then the determinant of this matrix will have to be 0. So if I call this matrix M, then its determinant has to be 0. Otherwise A, B, C, and D will all be 0. And that's not a very interesting wave to be considering. Okay. Yeah, these gammas come out from the derivatives. This is the matching of the boundary condition at the top, and well, the continuity of E and the continuity of the derivative of E. That's these 2 equations at the top of the film. So it's somewhat similar to if you have a particle in a box, then you're going to need to have a standing wave, meaning you get solutions that are half a wave, 1 wave, wave and a half, and so on. So that's basically what we get here, except now the boundary condition isn't that the field goes to 0 at the boundaries, it's continuous but decaying outside. Now, to get back to the determinant, it's one bloody calculation, but when the dust settles, we get that sine of gamma f d times gamma s gamma a minus gamma f square plus cosine of gamma f d gamma s gamma f plus gamma a. I'm saying one thing and thinking another. Gamma f. This should all be 0. Yeah, let's see. It's down here. I think that's the only one. Here. Yeah. There's one from the, when you take the derivative of the electric field, you get down a gamma, right? So this is from the continuity of the derivative of the electric field at the top of the film. Yeah. So that's where the gamma A came from. Okay, and this is pretty messy. So I multiply this by, let's see, 1 over gamma f square cosine of gamma f d, like that. You'll notice that the cosine goes away and I get a tangent over here. So after doing that, I will get the following tangent of gamma f d, and now I add a constant plus m pi, because you remember that the tangent is continuous, right? So I can just add any number of pi's and you will still get the same answer. That's equal to gamma s over gamma f plus gamma a over gamma f divided by 1 minus each of these fractions multiplied. That's gamma s over gamma f, gamma a over gamma f. Oops. Like that. Now, this is still not quite trivial to analyze. Unfortunately, it's never going to be trivial, but it's going to be a bit easier if we remember this trigonometric identity that tangent of x plus y plus m pi is equal to tangent of x plus tangent of y divided by 1 minus tangent of x tangent of y. Okay, so if I say that tangent of x is this quantity here and here, and tangent of y, that's this quantity here and here, then you see that these are on the same form if that's what it says inside here. Meaning that I can simplify this slightly. So when I perform the simplification, I get that 2 pi over lambda times d times nf square minus n square under the square root minus the arctangent of n square minus ns square. Now this is gamma s divided by nf square minus n square. This is gamma f minus arctangent of n square minus 1, because incidentally we were discussing air, but I could just insert Na here and have the air have any index of refraction, divided by Nf square minus N square, like that, should be equal to m pi. And because the tangent is periodic with exactly pi as its period, m will have to be an integer. So m can be 0, 1, 2, and so on. So when I said that n, the capital N was capital N was the index of refraction or effective index of refraction of mode m. Well, by that I meant that there is an index m on this capital N, which is of course given by this small m. And now, if you recall nm, that's omega over c times beta to minus 1. and beta was the wave number of the propagating wave. So this is the dispersion relation, except it's in a quite convoluted form because we can't explicitly solve for nm. If I could solve for nm, then I could write this as omega as a function of k or k as a function of omega. But as it turns out, I can't do that, unfortunately. So it's more of a numerical problem to find out what exactly are the group velocities, phase velocities, and so on. Also, I would like to make the following point, because m is an integer now. If we go back to this dispersion diagram with k parallel, or beta if you want, and omega, like that. Then we had a light line in air, the light line in glass, and the light line in the film. And we agreed that the propagating modes had to be here. So this is light line in air, glass, and film. Of course, the substrate and the air could be the same material, then these would fall on top of each other, but still it would be in this area that you would need to have the dispersion relation. But now, as m is an integer, this forms a line in this plane. So there are lines somehow for each mode. So one mode corresponds to one line here, one connection between omega and beta. If the film grows very thick, then we're back in the so-called geometric optics limit, where we can neglect the wave nature transverse to the film, and in that case you get a continuum here. But if the film is small, then you're going to see a confinement effect saying that you can only have certain modes in here. If you have a particle in the box and the box is huge, then you can essentially neglect the boundary conditions. But if you have a very small box, then they become very important. Okay. So this dispersion relation, it's very hard to analyze analytically, but it turns out it's not so hard on a computer. So I plotted this dispersion relation for you. And it looks like the following. Let's see. So, what I plotted here on the y-axis, that's nm. Let's see. So what I plotted is nm versus the thickness of the film d. In fact, that's most easily done by plotting d as a function of nm, but that's a different story. So if you have a look at this, if d is 10 micrometers, and the wavelength I used was, let's see, that was that of a red helium neon laser. So that's, I forgot to put that on. So that's 633, or 633 nanometers. So it's typically a red laser, like the ones you use in the optics lab. And then you can see that if I go down in thickness, let's say I take this d equal to, what is it, 1.35 micrometers. Then I only have, in fact, 3 modes. Because if you plot this further down, you see that the line stops here. If you go further down, there's something imaginary in here, and you basically get something not real out. That is, it's no longer a propagating mode. So only on these lines, which terminate down here and continue to infinity up there, only on these lines is your wave propagating. And now if I chose this d equal to 1.35, then we see that we have 3 crossings here. So we have 3 propagating modes for d equal to 1.35 micrometers at this wavelength 633 nanometers. Okay, so if I make my film thicker, I have a larger number of propagating modes. There should be several lines here as well. If I make the film thinner, I can in fact only have one mode that propagates. So even if there is a finite space here, you should think that there are many propagating modes, but in fact there's only one. So it's more similar to a particle in a square well from quantum mechanics, where if the well is small in some sense, then you can only have one particle stuck in it. And that's, while these are classical waves, of course, you can only have this one mode propagating if the film is thin enough. Notice that as d increases, all of these lines converge towards 1.674. That's the index of refraction of the film I used. Just pull out of a hat. You see that all these lines converge to this value as you go up here. This means that then we're back to the geometric optics, where you can just think of rays bouncing inside. Okay, so in that case we can more or less neglect the wave effects of having a finite transverse size of the film. Okay? Then so if the film is thick, those effects go away and we just see bouncing rays. And in that case, Nm is just 1.674 for all the modes. So it's like having a wave travel through, just traveling through glass, a large piece of glass, or some other material that lets light flow through it. So I think we stop for questions now. Nothing? Well, in that case, yeah. That m is to integers?
No, to smaller than the distance, like you said. For this dotted line, I have only 3.
This d is just an example.
Yeah, but where does it show in the equations explicitly how it's constrained?
Well, as you can see here, you can't really see that from these equations since they're so convoluted. But if you go to the textbook, and then you consider the case where you have microwaves in a hollow metal waveguide that's rectangular, which is a few centimeters on each side, like this. If you consider the propagation inside here, you'll see you can actually explicitly solve for the so-called cutoff frequencies, which we called omega mn. We did that on the lectures, right? So you have some quantization in this direction, you have some quantization in this direction, and then you need a certain frequency of the incident light to be able to excite this mode. So then you can see, then I think you see the same effect there. It's a bit, I mean, it's a different system, but the physics is basically the same. So you should see the same effects more or less. So, but here it's, since you can't solve for it analytically, then it's perhaps better to plot it or to perform some numerical considerations. Anything else? Yeah.
I would say that for the two cases where we said beta square is bigger or smaller than n square, omega square divided by c square, if there's a possibility where beta square can be equal to this.
Yes, that's sort of the limit case in a sense. But then you would get a constant, wouldn't you?
You would get omega gamma equal to 0. What does it mean?
If gamma is equal to 0?
Yeah.
Well, so if you consider it's perhaps easier, it's mathematically identical if you consider the particle in a square well, and then in the limit you would have that the wave function is constant inside. There's no wave nature. So it would just barely be bound. It's a very impractical case, right? So you can't really, if you wanted to do an experiment on this or use it as a communications tool, then you would have a mode that would just barely be propagating, and if there's some slight irregularity in the film, it would start propagating outside, right? It's technologically unimportant because it's so difficult. But in principle, there is a solution for that. You can just insert into the equation, you get, let's see if I have a sponge. So what you're saying is that gamma is 0, and then you have dx square of E2 of x1. Well, that's equal to 0. So it's a linear function. There's no curvature. So there is a mathematical solution, but it's not so technologically interesting. I had something I was going to say, by the way. Yeah. If you want some more intuitive picture in your mind when you're thinking about this, you can consider that of geometric optics, right? So if I have the film interfaces here, and I send in light here, well, then there is a finite angle here, which is the, let's see, this is the angle of incidence on this interface. Let's say theta I. If there's a theta I where you have exactly total internal reflection, right? So if theta I is gets smaller, that corresponds to increasing m. And then if m is large enough, the light can go outside again. Right? So that's the geometric picture. In fact, from each reflection here, you get a small phase shift. And you can, in fact, derive the dispersion relation from that, because in order to have a standing wave, well, then you need a certain phase shift compared to this phase shift from propagation on each bounce in order to get a standing wave. So if this is more clear to you, then think about this geometric picture, because it gives you the basic idea. And then if you have a larger and larger, a smaller and smaller angle of incidence here, then sooner or later the wave goes outside and you don't have propagation in the film anymore. Or, sorry, you have propagation in the air or in the substrate. Okay? Any more questions? Okay, then we continue in 10 minutes with the repetition of the course.